Hi, we got an equilibrium past paper question for A-level chemistry year 2 taken from the AQA specification. You will need a calculator if you're going to have a go at this. So there's the equilibrium for this question, SO3 in equilibrium with SO2 and O2. We're told that the equilibrium mixture contained 6.08 grams of sulfur dioxide. We need to calculate the mass in grams of oxygen in the equilibrium mixture. So we have to note that we started off with only SO3, only sulfur trioxide. So at the beginning of the equilibrium we had SO3 and we had 0 moles of SO2 and O2. So we can work out the amount of SO2 and we can work out the amount of O2 from that. And then from that we can work out the grams or the mass of O2. So the amount of SO2, we can use the equation number of moles is equal to mass over molar mass, and we can get to the amount of oxygen because we can see that it's a 2-to-1 reaction, and then from that we can get the mass of oxygen, the grams of oxygen, by multiplying the amount by the molar mass. So the amount of sulfur dioxide is 6.08 divided by 64.1, which gave me 0.04852 moles. As always, I like to keep a couple of extra significant figures in my process working out. Dividing that by 2 gives us the amount of oxygen, 0.047426 moles, and multiplying that by the molar mass of oxygen gives us that the mass of oxygen is 1.52. Don't forget that oxygen is diatomic, hence 32.0 grams per mole for oxygen. So here's the next part of the question as it was published. You might want to take a photograph of that or pause the video at this stage if you want to have a go. I've abridged it slightly for the next page. So I've taken just the key details to help us get to the point of this question, and we're going to start doing the working out now. So we can work out the mole fraction for each substance first of all by working out firstly the total amounts, 2.12 moles, and then we divide the amount of each of the substances by the total amount to give us the mole fractions. So the mole fraction of the 3 substances in the equilibrium are given by the amount of each substance divided by the total amount, and I've kept those to 5 significant figures. So next we have to give the Kp expression. So Kp is the partial pressures of the products raised to the stoichiometric coefficients divided by the partial pressure of the reactants raised to their stoichiometric coefficients. Stoichiometric coefficient is just a balancing number. So now we have to calculate the total pressure, and the maths can get quite tricky, so it's essential that you show your working out thoroughly. I've left the Kp expression there. Remember that the partial pressure is the mole fraction multiplied by the total pressure. So I've used the variable x to signify the total pressure. Substituting in the value for Kp there, given to us in the question, and the mole fraction of the SO2 from the previous part of the question was 0.56604. So the partial pressure is that number multiplied by the total pressure, and because that term is squared, I've got squared on the outside of the brackets. Then we've got the partial pressure of oxygen given by the total pressure multiplied by the mole fraction of oxygen, so x multiplied by 0.28302. And then the bottom term is the partial pressure of SO3 squared. So that's the mole fraction of SO3 multiplied by the total pressure squared. We now can work out the term a little bit more in detail by multiplying out the brackets. So just take care when you're multiplying out square terms brackets. So we've got the 0.56604 squared multiplied by x squared by multiplying out those brackets, and on the bottom it's 0.15094 squared multiplied by x squared. We've got an x squared term on the top and the bottom of the terms on the right hand side there, so we can divide through top and bottom by x squared to get rid of those terms. And you might also want to multiply out those numerical terms just to get straight to the numbers. So now we just have to solve for x. So rearranging that gives us x is equal to 191450 pascals. So the next part of this question gives us a different temperature and the value for Kp. So we need to look at how the value of Kp has changed, and from that we need to explain how we would deduce that the forward reaction is endothermic. So at the lower temperature, Kp is smaller. The larger the value of Kp, the further the equilibrium lies to the right. So at the lower temperature, Kp is smaller. So at the lower temperature, equilibrium has shifted to the left. Okay, so the final part of this question gives us a slightly different version of that equilibrium expression. The previous stoichiometric coefficient gave us those squared terms, but if we look at the equilibrium given to us in this question, we've divided through by a factor of 2. So the Kp expression now becomes P of SO2, the partial pressure of SO2, multiplied by the partial pressure of oxygen raised to the power of a half, all divided by the partial pressure of O3. Raising something to the power of a half is taking the square root of that term. So if you take a look at each of those terms, compare the red and the blue of the Kp expressions, we have square rooted each of those terms. So the square root of SO2 squared is just the partial pressure of SO2. The square root of the partial pressure of SO3 squared is just the partial pressure of SO3. And the square root of the partial pressure of O2 is the partial pressure of O2 raised to the power of a half. So to get to our value, we just have to take the square root of our Kp value at that temperature. So it's the square root of 3.94 times 10 to the power of 4, and that will have units of pascals to the power of a half.